We now talk about collapse patterns. We want to focus on potential location for victims and survivable voids. As you will see, these patterns indicate, in some cases, easily survivable voids, but in some cases, it is very difficult for individuals to survive in some of these collapses. NFPA 1670, as we talked about, has listed 5 collapse patterns for years. These were based on World War II aerial bombing damage, but they are still good today in that they indicate and are a communication tool as to what kind of a collapse it might be. These buildings were, for the most part, based on ones with unreinforced masonry walls and wood floors, so one gets the floor panel, if you will, making voids. In the upper 3, the lean-to, the V, and the A-frame collapse are all similar. And with those, one would expect to find victims at the bottom of the slope of the floor because they started on the floor. They may be above the floor in the debris that's collected as the floor, they would be sliding towards the lower edge, or they could be below the floor where the space has been confined and could entrap them. These pictures show relatively regular planes, but there'd be a lot more debris. Things that would make victims little voids there'd be furniture, heavy furniture, especially with wood floors, could create little void spaces. With pancake and cantilever collapse, which are shown at the bottom, the cantilever, of course, is similar to a pancake in that in a cantilever, you just have a part of the structure sticking out like a diving board, which is a cantilever. In those cases, with wood structures, the voids, the victims, of course, start out on the floors, are going to end up on each of the floors, and the survivable void spaces will be created by structural elements that stick below, like deep beams in concrete structures, or in wood structures, heavy furniture, kitchen cabinets, especially the lower cabinets, refrigerators, things like that will all create voids. And by the way, they're also good places. The kitchen is also a good place as a safe haven in the case of a collapse. So in the case of concrete, of course, the voids will be more difficult to create, and so it requires much heavier and stronger material to get in the way of planes that are collapsing to form these voids. And the victims will be found in those voids and have been, as we'll discuss. We're going to talk about various kinds of collapse patterns, but first we're going to talk about those that are caused by earthquake. Basic things about earthquake is that earthquakes they're not forces. Earthquakes provide shaking, and this shaking causes the damage in the structures, as has previously been discussed. So that the structure gets damaged. Normally, it's the vertical support elements or the walls that are providing the lateral resistance, the shear resistance. That fails one way or the other, and then gravity takes over, and as the structure has lost its vertical support, gravity will cause the structure to collapse. And if the structure has redundancy or ductile behavior, it may be only partially collapsing or prevented from collapsing, but if it's a very brittle structure, that would enhance the possibility of a complete structural collapse. Again, repeating, survivability in earthquakes has been sufficient to save many, many victims for as long as 14 days. This same little diagram we've shown earlier. So that, but again, we talk about the golden hours of the first day, the first 24 hours or maybe 36 hours, where one wants to find most of the victims. Within the types of buildings that we've talked about so far, we want to sort of recategorize them for earthquake and look at the collapse patterns for light frame structures, where we'll see an offset collapse pattern, which we'll explain. And then with heavy wall buildings, such as unreinforced masonry, URM that is, and tilt-up, low rises with concrete or other masonry walls, it's a wall fall collapse pattern. These are new collapse patterns that we've defined here. And then with heavy floor, which are concrete buildings for the most part, we'll see a pancake, which we've talked about, but also an overturning or a soft first-story collapse, which is sort of a special pancake, if you will, only one layer. And then with precast buildings, which are fairly heavy floors and heavy walls, the best that we can come up with is a random fall collapse, because that's what happens. So looking at the light frame collapse pattern, the reason that a light frame building collapses the way it does is because of the way it's built. It's unique in its construction type. That is, the walls are made of skin and bones, that is, the skin being the sheathing and the bones being the studs and the columns. So what happens in an earthquake, the building shakes, the walls become racked, the sheathing strength is overcome, and the structure starts to move laterally. The studs are still capable of holding the structure up there, so they're not going to allow the structure to pancake on top of itself, but what they're going to do is cause the structure to offset. And so if you have a single-story collapse, the upper part of the structure will offset by one story. If you have a two-story collapse, the upper stories will offset by two stories. This is important when we talk about where the victims are, because if we're in the safest strategy, we want to be in the upper story where we still have a fairly viable space, and we want to cut down to get to the victims. Well, we'll know that if we're in a building that has stacked bedrooms, that is one bedroom on top of the other, that if we're in the upper bedroom, we're really 10 feet or more or so away from where the victims are below us. So that becomes very important. And the victims will be found, for the most part, in that collapsed space underneath that is in the first story or in the stories that are collapsed. But also victims have been found in the upper stories where they've been thrown about, they've had broken limbs, they've become hurt, and they're down, and can be found often, and in a lot of cases they're able to respond. So this gives you an idea of where this building is going. The other thing about this offset collapse is that a building has to have some place to go if it's going to collapse this way. And so normally they're buildings that they're on a corner, or they have space next to them, and so they'll go in that direction. A building that's in the middle of a block where it's all the buildings are next to each other, it might have the same kind of damage, but it can't go anywhere, and so it may be not collapse. This is the example from the Marina District in San Francisco of this kind of a collapse, where in this case it was a three-story building. The first story had a parking structure in it, so that it was very, very weak. It was wood, all wood. It was built in 1925, and so the kind of sheathing that it had was just parallel sheathing, very weak. What you see here is the result of what's happened. That building in the upper picture at one time was vertical, and the wall was all aligned with the wall that's to the right there. So that you have first story wall that's laying almost flat. The second story wall is standing, but it's 10 feet away from where it used to be. And the third story wall is standing, and it's away from where it used to be by maybe 15 feet. So the structure has offset. One looks at this structure and said, okay, how would I approach this? Is this structure stable? My answer to that is no, it's not stable, but it is at rest. So unless there's a very violent aftershock, it's probably not going anywhere. And even if there is a violent aftershock, it's probably, the upper part is probably going to stay intact. So one would enter through the upper space of which is now the third story, and try to get to victims that are below. One would, of course, when doing that, would have an escape plan, would have some idea where a safe haven within the structure would be, and it would not be, one would not enter the void space except with few people, with minimum exposure, only when a victim was found, and only for a short period of time between aftershocks. One could do some shoring, but again, if the victims were badly hurt, one might not need to get in without that. So victims are going to be found in the upper space, but mostly in those two collapsed stories. Pretty easily accessed in wood structures, and pretty easily found because sound will travel through, the scent will be easily found by the canines. And by the way, canine are meant to be sent into those spaces from the side of the structure. Just another example of an offset collapse in a little more mundane structure. That is, when you have a split-level house, you have sort of a built-in weakness where stories are offset. If they're not well tied together, one can get a collapse of one off of the other. There are a couple examples. The upper one, the story has not collapsed yet, but in the lower one, you can see the outline of the roof from the right on the structure at the left, which was over a parking or two-car garage. In that case, victims could be found in the collapse below, but also could be found in the space above, again, from having been thrust about and fallen down and injured. Next type of collapse pattern is that with heavy walls. These buildings could be, again, URM, tilt-up, or any low-rise building that has a heavy wall made out of concrete or masonry units. In this case, the earthquake shakes the building. The connection between the floors and roof and the wall are broken, and the gravity forces that are generated then in the wall gets offset. The wall then gets thrown to the ground. And URM is a little different than tilt-up, whereas in URM, the walls rarely project themselves the full height of the wall, but often in tilt-up, of course, the walls would do what we would call a 90-degree collapse. That is, 16-foot high wall would end up 16 feet. The top of it would end up 16 feet away from the building. Victims in this case, the very, very badly injured victims, would be outside of the wall. And the earthquake slogan of duck, cover, and hold was developed for just this kind of building, where you don't want to run outside of this building as it's collapsing, because you would get in the way of the collapsing wall. The spaces inside the building often are formed for survivable voids, and so that's where you would find some victims inside the building in whatever voids are left, and you could also find them, although mostly dead victims, outside underneath the walls. Another picture of the collapse. The way earthquakes work, of course, is that they shake the building, and the higher you are in the building, the more forces are generated, and so it's more likely that parapets would fall off first, second-story walls second, and so forth. But in some cases, you do get the entire wall collapsing into a big rubble pile. Again, it indicates there where victims might be found within the rubble outside, but also inside, and the inside ones are in much more survivable void spaces. Here's an example from Kalinga. There's the upper picture is from Kalinga, where you can see, we're going to look at that building again in a minute, and you can see on that block how in some cases the parapet fell off, and in some cases the parapet and the second-story wall fell off. Then there's the one from, actually it's northern Italy, where the entire face of the building fell off. So it really doesn't, and that's stone masonry, if you will, rather than URM, but it's still the same kind of material, and it still performs very, very badly in earthquake. But you can see how survivable some of the area was, and there will be many victims or occupants, if you will, that would have self-rescued from that space. So looking back to this building from Kalinga, it is really a good study of two buildings. One, the one on the corner, where you see the fact that the property line wall has collapsed and caused the building with the truss to collapse into what we would call an A-frame, or excuse me, that's a lean-to collapse. But the roof of the building on the corner hasn't collapsed because little catenaries have been formed. The redundancy of just having the plaster ceiling has held up that very light roof, of course. So there's lots of survivable spaces in that corner building, as you can see here in the lower picture. But also in the upper building, where with the truss and the lean-to collapse, trusses are not the best structures in the world, but on the other hand, they can span large spaces. So in this case, it has formed a lean-to collapse where victims are probably going to be found below the truss at the lower end of the slope. But they could have also fallen out of the building on the corner and could be above the truss as well. I have to, without going further, I have to mention that you notice the large refrigerator that's in that picture, which is a potential safe haven in a building. It's also something that's going to form a void space, as well as all sorts of things that are in that building. So again, fairly highly survivable voids in this kind of construction. It's relatively light. Here's a case where there's more of a complete URM collapse, where that lower story victims, there may not be voids, but again, the upper stories, good chance of survival, and the victims can be located outside the building as well as in those spaces. And the the voids formed by all sorts of material that's occupying the structure, heavy desks, refrigerators, and that kind of thing. Heavy wall fall collapse pattern for a tilt-up building is a little different in that, in this case, the spans of the structure are greater, and so the potential for larger collapses is there. The minimum span in these kind of buildings is normally about 20 feet between beams, and the beams will span 50 feet or more, so that if a wall falls off, the roof is likely to collapse in some sort of a lean-to. And in that case, if there's a roof only, the victims are going to be found below that roof at the lowest end of the slope. And if victims are found outside the wall, it is very, very likely that they will be dead because of the great weight of the wall and the fact that it falls pretty much intact. And unless there's something outside, like some cars or like that, one might be survive if one was between cars or even in a car, possibly. This is an example of how a little bit of redundancy kept this building, it's a tilt-up building, and in the front wall you see these little fins that stick out. It doesn't look too bad from this view, but if we look at the next picture in the upper right, you'll see that the roof is actually not attached anymore. That's the front wall, and what has happened is that the earthquake caused the wall to move out, separate from the roof, and then move back because it had those little fins, and the roof is just barely hanging up there by a thread. And didn't collapse. And on the other hand, the picture in the lower left, the wall did collapse, or the roof did collapse when the wall moved out, perhaps injuring people. And again, in this case, you can't see the rubble below, but victims could be found there if there were any. But the lesson here is that in this relatively small building, a catenary was formed to keep the wall from collapsing, and it was a horizontal one. So the wall just did a big bow, and because of the reinforcing that's inside of the wall, it's kind of, if there's any kind of a way that a structure can resist collapse, it will. A couple of more examples. The lower one just shows how redundancy at a corner will help the collapse. You can see also the redundancy of interior partitions that are forming the voids inside where one could find the victims. And then at the very, very bottom, you see the panel, the wall panel that has collapsed, and it's just flat against the ground. And so the likelihood of survival beneath that panel, and also the likelihood of there being victims there or people there before the collapse is very, very low. The upper picture is a corner where the structure did collapse, and then the part of the roof collapsed. And again, the victims would be located below that collapse. In the case of heavy floor, which we're talking about concrete buildings for the most part, and it's concrete frame buildings where they don't have many walls, and all the lateral resistance is achieved through the interconnection of the very strong columns and the floor. And outside of California, previous to about 1980, many buildings cannot withstand earthquakes of this type, and so when the joint between the column and the beam is overcome, the gravity forces within the floors will drive the structure essentially into some form of a pancake for the most part. We'll see that, and we'll see also some other kinds of things that can happen to these kind of buildings. So this is the before and after of a pancake collapse. In this case, survivability is possible. And again, in earthquakes, since it's the columns that are collapsing and the floors are just dropping, so that very strong concrete floors, kind of the good news is that they're very, very heavy and they can kill people. On the other hand, if there's any kind of an element that gets in their way, voids can be created. And so that's where the victims are found. In the 880 freeway collapse from 1989, many survivors were found because of just the configuration of the structure. The upper floor collapsed on the second floor of the freeway, but the lower picture shows the squashed car, but because the beams struck about 3 feet below the slab, and the slab is about 3 feet thick, there were many, many survivors. As long as your car didn't end up underneath the beam, many people survived. About 40 survived in that structure. So the pancake collapse happens to these heavy floor collapse patterns, and as we've already discussed, victims will be found in the void spaces if there is some kind of, in this case, very heavy and very strong element that will form a void. This is from Mexico City, my Mexico City experience, where many of these, about 40 buildings of this type collapsed, and about 150 victims total from all 40 buildings were removed. It looks fairly compact, but there were void spaces caused by pieces of masonry, parts of the columns that were forming void spaces. And in at least one case that we were involved in, it was a garment factory, and there were very large bolts of cloth that were able to form a void that saved a couple of people. So very difficult situation, but again, the potential is there to form the void space because you've got the very competent floors. Of course, the other side of that very competent floor is, in order to get to these victims, one needs to cut through the slabs. Normally we do that from the top. And that's why our system has developed a lot of training for rescuers using concrete saws and drills and so forth to be able to penetrate these kinds of structures. Canines, by the way, were able to get into those structures laterally from the sides. One thing that has happened to some kinds of heavy floor structures is that in some cases, they have overturned. In that case, the structure above the foundation level is pretty much intact, and of course, the folks inside of it may be injured. Cause of the collapse in the case of those buildings that were in Taiwan was a very poor connection between the foundation and the first story columns. So once that was ruptured by the earthquake, these buildings overturned pretty much intact. So you can see this, the spaces are there for people to survive in. They, of course, went through a very large, movement, and then they had an abrupt stop, so people can be very badly injured. But talking to the firefighters from Taiwan, many people were brought out of these buildings just using their hand ladders and aerial ladders, so that they're really very survivable spaces in this kind of structure. Another very common collapse pattern, both in some wood construction as well as concrete construction, is one of a soft story collapse. This happens when structure is really poorly designed. That is, the first story is so weak compared to the upper stories that the earthquake focuses all the energy in that one story, and it collapses, basically. And what you end up with is the upper stories pretty much still intact, where victims can self-extricate, or again, if they're fallen down, there may be a few there, but in this case, most all the victims will be found in the space in this one story. It's a couple of buildings from Taiwan of that type. The upper one is a schoolhouse that may look like a one-story building. At this point, it originally was 2 stories, so there's one complete story of schoolhouse that has been collapsed. Fortunately, this was at 1:30 in the morning, so that it was not occupied. Structure below was one that has 3 stories above, plus a little bit of a penthouse. And then the first story was commercial. The upper stories were living spaces. And so we had that mismatch in amount of walls and strength, and so these structures collapsed. And the victims were accessed by getting into the second story, cutting through the floor, and getting to the victim. Lastly, for earthquake collapse patterns, we have precast construction, and precast construction is the elements themselves are extremely strong. They're built in a factory, brought to a site, and connected together. And therein, as far as earthquake is concerned, lies the problem. If they're not connected together, very, very ductile and competent interconnections, including sometimes pouring a slab on top to connect everything together, they will tend to come apart. So the collapse pattern that occurs is one where the parts that start out as parts become parts, and it's pretty much random. So I'm calling this a random parts collapse. Victims may be found in any part of the collapse zone. The survivability based on historical data from the collapse of these kind of buildings has been very, very low, unfortunately, because the parts become very small, get broken, and there is no, you compare this with the heavy floor collapse where you have the large slabs. You don't have that in this case. You have just a lot of small parts and relatively small survivable spaces. This is one of the collapses from the Alaskan earthquake, where the large T roof collapsed, and you can see that if you're in the wrong place in this particular one, that the survivability is low, although there were survivors in this particular structure. You can see how the large T's form some voids and where the victims would be. Since this is only a roof, all the victims would be beneath the collapse. This is from Armenia, where they were multi-story, and you can see at the bottom the compactness of the collapse of the lower picture, or even more so in this picture. Survivability would be very, very low, and pretty much all the victims would be found within that very, very dense rubble. This is one collapse where a victim was extricated from. This is from the Northridge earthquake, 1994 in Los Angeles area, where at 04:30 in the morning, there was a gentleman in a sweeper truck that was cleaning this garage, and he was trapped. And fortunately, his truck provided him with a void, if you will, and he was rescued beneath the collapse here. Blast collapse patterns. They're very, very different from earthquake. Again, we think about earthquake, the vertical elements have been damaged, and so the floors pretty much come down intact and form voids. Hard to cut into sometimes, but nonetheless, voids are formed. In the case of blast, we have the devastating effect of on all surfaces of the structure of the pressure, and so floors are thrown about and thrown into the air and come down. And in addition to that, the blast pressure itself it is almost impossible for a human body to survive the direct force of pretty much of any blast pressure. So these pressures are very, very large, thousands of pounds per square inch in some cases. They're very short duration, and they rapidly dissipate with distance. They do severe damage to structures, mostly on the surfaces, and they also have a very fast-moving shock wave that can be very complex. And there have been people that survive in these structures if they just happen to be around the corner from where the blast pressure is acting. The blast pressure almost acts like a flashlight, if you will. If you're in the shade of the pressure, often you can survive. So everything gets pushed about, including forces that are acting upward, which is not the way buildings want to feel forces. So we want to look at the following: a wood, steel frame, some light steel, a little bit. I don't have any pictures of that, but also the focus a lot on concrete frame structures, a little bit on precast structures, talk a little bit about post-tension concrete structures, and a little bit about heavy wall structures. Again, reminding you that few survive within the collapse zone due to the blast and the crush effects of the blast just on the human body. So in wood structures, pretty much everything is blown away, and if you happen to be within the structure and within the blast zone, it is very difficult to survive, and what one ends up with is pretty much a pile of sticks. It looks very similar to what a tornado does to a building. In the case of steel frames, what has happened in the past is that the blast pretty much goes past the large steel beams and columns, but it will lift the floors up into the air, and then it'll pretty much drop them down to the lowest level of the building along with all the victims. So I'm calling that a lift and drop collapse, and you'll see that in kind of the next picture. This is a building from Puerto Rico. It actually is a concrete exterior frame, but the steel framing of the interior. And what happened in this case is that the floors were very light bar joist with light steel deck and a little bit of concrete fill, and all the floors were thrown up into the air, and they all ended up in the basement. So if you think about that, the survivability of the people that were on those floors has got to be very, very low, and in this case, no one survived. This is what was left then. We had the steel beams pretty well charred by the blast, but nonetheless, there's a steel framework of beams as the structure was lifted, the floor structure was lifted and then dropped into the basement. The effect on concrete structures of the lifting force of a blast essentially sort of goes against the way a so-called gravity design of a steel structure is done. One places reinforcement steel to resist forces coming from the top by the weight of the structure and the weight of all the things, the occupants that are on it and the furniture and so forth. But in the case of a blast, force is upward, which provides causes tension stresses to occur in the structure where there perhaps is not any reinforcement unless the structure has been designed for blast. And so you get this devastating effect of the structure sort of bending upward, cracking at the bottom near the ends, cracking the middle near the top, and the structure then gets lifted up, and then it collapses to the lowest level. Often what can happen in this case is that some of the vertical supporting columns might be left without any floor load on them, and they might be left standing many stories tall with still some load above them and with the chance of buckling, because they would now have, where they were originally braced every 13 feet or so by a floor, they might be standing 40 feet high without any bracing, and we'll show a couple of examples of that. That kind of thing happened in the 1993 blast in the garage of the World Trade Center, where the terrorists placed a vehicle right next to tower number 1, hoping to bring it down. They just merely dented a little bit one of the columns of that tower. But what they did do was that the garage floor slabs, which were relatively thin and designed for downward forces, were all lifted, and then they were dropped into the abyss of the basement, 70-foot deep basement, and so one had a 6-story hole there. Immediately what had to happen, of course, is that smoke filled the towers, and so the many thousands of people that were in the towers were all evacuated. And then the 20 or so that were in the basement had to then be addressed, or in the parking structure in the basement. So what was done in order to keep the vertical columns, which now had no floors, 6 stories high, they put in some steel braces, and then of course they got to the victims, who were pretty much all deceased at the lower level. Putting in this bracing in this case is to reduce the risk while you're recovering non-viable victims. That's what we do. We will take a little bit longer time if we're sure that the victims have perished. We can take the time to put in this kind of bracing. Oklahoma City bombing was a similar situation, where it's a concrete structure, not one with steel columns, and so it was even a little bit more difficult to deal with. In this case, there's this simulation will show you how the structure lifts and eventually gets up and collapses. And if you look very closely and want to run it a couple of times, you'll see that there's a couple of columns that are left standing 3 stories tall in the background at the second row in. So in this case, all the victims now that, first of all, in the first few hours, Oklahoma Fire removed all the live victims that were trapped because they couldn't get downstairs and so forth in the upper part of the structure. After 7 p.m. on the first day, no one survived. All the victims now are found in this giant rubble pile at many levels, and they were dealt with by the Urban Search and Rescue System as well as Oklahoma City Fire. Give you some idea of, this is after a lot of the rubble was removed. You'll see those 2 columns right in front of you there that are standing, they extend from the ground up to the 4th story, where they used to have bracing. We had to add bracing in order to keep them from collapsing as the rubble was removed. In order to get to the nursery was within that space, and that's where the 19 children were found. Unfortunately, all did not survive. To give you some idea here, then, what survivability in a blast is, there were almost 360 people in the building. 168 of them were killed, and almost all of those were within the collapse zone. There was an additional 1 volunteer nurse that arrived the first day without a helmet and was killed by a falling object. And as previously mentioned, all the live persons were removed by about 5 p.m. on day 1. So very, very difficult in a blast. First of all, people are thrown. In this case, they were thrown 30 feet or more in some cases, killed by the impact, killed by the blast. And then the lift and drop collapse of all the material coming on top of them. None of it, or very little of it, capable of forming much of a void, because the slabs themselves were pretty well broken up. Very, very difficult situation for survivability. Blast effects on precast concrete. I have a couple of structures here to discuss. First of all, in a frame type structure, pressures will dislodge panels, again the walls and panels, and depending on kind of interconnection there is, the building may or may not survive in good enough shape to form voids. In some cases, these buildings have, the tall ones, there's been a progressive collapse where many stories have collapsed on top of each other. In the case of a box-type structure, there's, again, much redundancy in those structures, and I'll show the example from Saudi Arabia where the structure responded very, very well and few victims were killed. This is the Khobar Towers, a box-type precast building from Saudi Arabia where the explosion killed 19 and injured 400. Very large explosion, similar to the one from Murrah Building in Oklahoma City. But in this case, due to the fact that it's a highly redundant building with very good connections, only one face of the building was collapsed. And you can see the corners collapsed a little bit around the corner, but the structure is pretty much intact, and the ability to search in it is still available. You can still get up the floors and remove people and so forth. And so in this case, only 19 were killed because it's a highly redundant building. So I have this little comparison here. So if you compare the Murrah Building, where you have about the same number of people in the building, it's very brittle. The concrete was brittle. It was anti-redundant in that on the wall face where the bomb exploded, the columns originally were at 20 feet on center. By the time they got to the third floor, there was a large transfer beam, and so that the columns were 40 feet on center in the first story, so that when the blast destroyed two of them, you got a blast zone that was, or a collapse zone that was 120 feet by the first bay in, which is about 35 feet. So 45% of the building collapsed. There were lots of falling hazards, and there were 169 killed. In this case of Saudi Arabia, highly redundant building, only a 10% collapse, and that's probably on the high side. Lots of falling hazards, 19 people killed. Many people were hurt by glass shards and flying objects, but they survived. So it makes a whole lot of difference if the structure has redundancy and ductility. But again, in both cases, you pretty well know where the victims are in these situations. So lastly, blast effects on other kinds of structures, tilt-up, reinforced masonry, unreinforced masonry. Because they have these large panels of walls and roofs, you would expect that the panels would be blown off, especially light roofs in URM and tilt-up, and then the walls might be blown out. You can see in this case how this wall is being restrained. Part of it was blown out, and it's being restrained by what we call a tieback, and then the floor was pretty much blown away. This is from the blast from across the street from the Murrah Building. There were 3 or 4 victims that were found in this building, and they were all found in the collapse zone.